Welcome to the first meeting organized on a scientific subject, NETLAS. We should have more of such events, and we appreciate the fact that RECENT and Ivan and Bettina volunteered to open this sequence of scientific presentations. RECENT is one of the 6 associated partners to NETLAS, and as we all know, the title of our Marie Curie doctoral school is Next Generation of Tunable Lasers for Optical Coherence Tomography. In one way or the other, each project within our network will have something to do with OCT, and RECENT is a champion of applying OCTs to all sorts of directions, of which I'm sure you will see in this presentation. I haven't seen the presentation. I'm sure you'll see those aspects. I was impressed. Last time I visited was a couple of years ago, and they do great things, which I'm sure will be very valuable for our interactions. So that is about the event. I will ask the supervisor of Ivan, Dr. Bettina Heise, to introduce the speaker of today. So Bettina,
yes,
please.
Thank you. I briefly want to introduce Ivan Zorin. He is my colleague at RECENT and is a member in my group, partly in the OCT group. On the other hand, he is also included in the spectroscopy group. So from his biography, Ivan comes from Russia, from the southern part of Russia. He studied then in Petersburg at the famous ITMO University and did there the master, first the bachelor and then the master in this ITMO program in laser technology on biomedical imaging. This university has also close cooperation to Finland, to the Eastern University of Finland, and that a joint master program in photonics exists where Ivan did his master in the field of wide field adaptive optical microscopy. In this connection, he was also several times at Delft University under the supervision of his supervisor, that was Professor Klepf-Dorwin. And that was also the point where I met once Ivan in a summer school for adaptive optics, and once together with his Professor Klepf-Dorwin and him, we somehow convinced him to apply for the SuperVIA program and projects that was also in ITN, similar to yours. And he was one of these ECR students in the SuperVIA project. That was a jump from microscopy, adaptive optics, to field of mid-infrared imaging and spectroscopy for him. He did his PhD, I think it was last September when he finished and had his defense. And since that time, he is as a postdoc here. We have a follow-up project where he can, let me say, extend his expertise in mid-infrared OCT imaging and finding also improved solutions there. Yeah, that is more or less the current state, where we have local cooperation partners in this project here with a ceramics additive manufacturing company, and on the other hand with some supercontinuum source developer, and so that is at least one field of his activities in the moment. And I think that it has a bit of connection also, at least in NETLAS, there are also new sources and technologies for OCT should be developed, and I had the hopes that we can build up a bit an exchange of our expertises, and therefore, yeah, I'm also happy that Ivan agreed to give the talk today. So
good.
Yes.
Thanks, Bettina. Now, Ivan, you have the floor, so please start.
Yeah, thank you, Adrian and Bettina, for introduction. Yeah, I will switch to the slides already, and will tell you about our activities in mid-infrared OCT here at RECENT. And I have quite a lot of slides, so maybe some of them I will skip. But if you would have questions or something, we could go back to them. So I will just shortly introduce RECENT. We are located in Austria, in Linz. It's kind of halfway from Vienna to Salzburg, at the campus of JKU University. It's the University of Kepler, Johannes Kepler University. And RECENT is abbreviation for Research Center for Non-Destructive Testing. And we have 2 areas, so it's optics and acoustics, and 6 research groups. And of course, I and Bettina, we belong to optics. I work in OCT group and partly also in infrared and Raman spectroscopy. That's why you will also see just a little bit of spectroscopy today. Yeah. So RECENT has an expertise in several topic, and first of all, it's non-destructive testing, of course, of materials of different kind, but mostly of technical nature. It's quality control, inline, online monitoring, prototype development of sensor and systems, and of course some project management and technology management. Yeah, this slide was proposed by Bettina, so just to show some history of collaboration between the group at Kent University and RECENT. So first of all, it was Shape OCT. I was even in one of the meetings there. Then currently it's NETLAS, and I think Bettina was visiting this conference on OCT 2 years ago, 3 years ago. Yeah. And also some examples of applications in OCT, with which we are working. It's mostly, as I said, non-biomedical samples applications. So it's investigation of bright scattering from sometimes materials and like plastics, coatings, some crystals, birefringent materials. So that's where we have expertise in OCT. Yeah, and just to introduce me a little bit more, and I would just show some old slides from the project, from my Marie Curie project. So I was a part of SuperVir. The project was about supercontinuum sources with particular focus on mid-infrared supercontinuum. So here are some institutions, maybe you might know some of them. I guess NKT is also in your project. And yeah, I was working mostly on an application side to apply these sources for OCT and spectroscopy. That was my task. And some photos from one of our meetings that were still online. Not online, on site, yeah. And yeah, here I would start the main part, and I would like to start it from motivation, actually, and just going back to 2017, where I started. There was the paper of Rongsu, he published in 2014 about perspectives of mid-infrared OCT. Of course, it was considered for technical samples because of water absorption, and he performed Monte Carlo simulations and generated OCT images of potential performances of OCT in this spectral range. And he could demonstrate that it might have and should have better penetration depths. For example, compared to our standard 1.3 micron OCT and 4 micron OCT. So, and yeah, it was done in 2014, and actually there were no experimental verification of these simulations because mid-infrared is quite challenging. You can't simply transfer OCT technology to another range. So, and there are several reasons for this. There were several reasons for this. I will maybe shortly discuss this. But for example, I give here, it's this camera I had for testing at the beginning, just to try to make some OCT imaging with this, because it's only 320 pixels. It's MCT camera, mercury cadmium telluride detectors. And this camera costs around 50,000 euro. So that was kind of a problem with detection. Yeah, just some simulations also to reveal this point of longer wavelengths for OCT. So it was simulated by me in Zemax, and so it's more or less me scattering simulations, where you can see that going to longer wavelengths can significantly enhance problem depths, while for shorter wavelengths, multiple scattering would dominate. Yeah. And yeah, back to 2017, there were already system reported at 2 microns, so it was kind of internal motivation for me that could already show the results with like enhanced probing depths, but in the field of art inspection. So it's a group of Heider-Young in Nottingham. Yeah, so that's what we had at this time, and the changes were like the light sources, but fortunately in the project I had a light source to do that, and another was detection, another issue. Yeah, let's start with sources. I think you should of course know what supercontinuum is. I just shortly tell this. Yeah, supercontinuum is actually already quite well-known phenomena. So it's reported first in 70s and got its name maybe 10 years later only, but more or less it's generation of the broad spectral continuum, which is what we need in OCT. And yeah, since this time this evolved quite a lot, and probably the big step was that it's now generated in optical fibers, where we can concentrate our energy in a very small core and a long distance, which is of course good for nonlinear phenomena that are happening here. And yeah, finally we have this complex evolution of the pulse in spectral and the time domain, and the spectra that we want to have for OCT. Yeah, and in our project, this technology was already it was developing in the mid-infrared. So of course the new fibers suitable for mid-infrared generation were developed new schemes, like these cascading schemes shown here. Yeah, so the sources I already had at this point, and in my research and development I used this Tiblan supercontinuum source with a spectrum shown here. So it's just a basic scheme and how the generation of supercontinuum in fiber happens. So we have the short input pulse at around 2, and then it broadens. Yeah, and for OCT imaging, in my case, I used actually this peak at around 4.1 microns. Yeah, that's about sources for OCT imaging in this range, and now I will just tell another like side effect of mid-infrared. It's spectroscopy. So the goal was not only to have OCT imaging, but also have some combination with mid-infrared spectroscopy. It's another non-destructive testing technique that actually probes vibrations in molecules, and these vibrations, they have well-defined energies, and they are subject to quantum optics, and Yeah, so this spectra, molecular spectra, are such like individual for some chemical components, like atomic spectra for elements, and you can identify different. So you can identify chemical composition of materials by doing this. And yeah, this is kind of quantification, qualitative analysis. If you would see such spectra and have some experience with interpretation, you can identify the structure of molecules you're probing. And for quantitative analysis, the Peirce law is used. It's just to analyze the intensity of absorption, and this can be linked to concentration, if you know, of course, the path lengths and direction path lengths. Yeah, so different molecules vibrate differently, and this the energy of vibration can be probed. So if our wavelengths are in resonance with the vibration and there is a change in dipole moment, then there would be absorption event, and we can track this using some spectrometers. Yeah, for example, there are symmetric stretching, asymmetric stretching. So asymmetric needs a little bit more energy because of its nature. And yeah, there is also rotation of molecules, but it's already longer wavelengths. In mid-infrared, there's like bond stretching and stuff like that dominates. Yeah, and here there was also to consider which spectrometer to use. There are the different types of spectrometer. So, but here I just wanted to show that actually there nothing changed really from the scheme of Kirchhoff-Bunsen spectroscope, which was this dispersive element. So the spectrometer I used was also a dispersive spectrometer. It could be also tunable systems, and maybe what is really different is Fourier spectrometers that are actually quite similar to OCT. They are just different unknowns. In OCT we know spectrum, and here we don't know spectrum, but it works similarly. Yeah. And why actually supercontinuum sources were interesting for spectroscopy is because of their brightness. So brightness is actually like power emitted into a certain direction per unit surface area, per unit solid angle and wavelengths. So, and from this point of view, supercontinuum they offer really new capabilities because they are broad and also have quite high spectral brightness. And in this case, we can extend our interaction path lengths, detect lower concentrations, and so on. Yeah, and if you design spectrometer, you have kind of geometrical parameter of spectrometer. It's called optical throughput. It's more or less like NA or something similar. And if you have brighter source, of course, you would have more energy to probe your samples. So that's why it was interesting for spectroscopy, and we were thinking how to combine them together with OCT. And of course, the most like straightforward and logic way is to use EXIF hyperspectral imaging to combine them in such a way that we probe the sample with the same measurement head and then separate the OCT and spectroscopy parts. Yeah, here it has to be mentioned that supercontinuum have quite good spatial coherence and beam quality. So this my characterization for mid-infrared NKT source, it has m square below 1, and yeah, that allows us to get near the diffraction limited resolution. Yeah, so as it was shown, for example, in this publication, it was purely spectroscopy paper, but which then was like extrapolated further, and similar concept was employed in OCT in my case. So here it was possible to resolve individual blood cells and measure spectrum on them. Yeah. Now I will just very shortly tell about detection in mid-infrared. That was like a main challenge. since we have sources, as I mentioned already. And here it's quite problematic, first of all, because there are no really arrays or linear arrays cameras in this range, and detectors are significantly less sensitive in the range of interest. So if you are around 4 micron, you can see that what we really would have, it would have a significant low detectivity. So detectivity is reciprocal to noise equivalent power. And for example, indium gallium arsenide detector at room temperature in near infrared would have detectivity by several orders of magnitude higher. So for comparison, detector I use now has detectivity of 10 of power of 10 at room temperature, and that's already quite good for this range. But 3 years ago, I did not have any semiconductor detector, and what came to my mind first is to try to use thermal detection, and here for this range, Pyroelectrics offer actually quite good performances, and I was using lithium tantalate detector, which has quite good detectivity. Yeah, and just the principles of pyroelectric detection is simple. So the radiation is being absorbed by some by actually some blackened surface of this crystal, pyroelectric crystal, and then we can see the changes in spontaneous polarization. So the interesting thing why I like and don't like this detection is that it's AC detection, so it's sensitive only to the changes. So that's why you have to modulate this, but also it gives us very interesting features for OCT. Yeah, and the first demonstration was mid-infrared OCT with supercontinuum source and with this pyroelectric detection. So this is the principal optical setup of what we had this time. Yeah, it's of course free space also because it's quite challenging to make it in other way in mid-infrared. So the spectrometer is quite simple, just grating, and also yeah, the mirror optical is needed to avoid chromatism and this pyroelectric detection. So this is how pyroelectric linear array looks like. If you remove the cover, here are the sensitive elements. They are rectangular shaped, which is good for spherical mirrors because we have astigmatism due to this. Yeah, and actually it was the first or half of second demonstration, it's difficult to say, but we could already show some enhanced penetration depths into certain types of materials. So here is just the comparison of mid-infrared at 4 microns and at 1.3 microns. This is some paintings mock-ups, so it's oil paints. And usually they contain pigment particles, which then makes these materials very scattering. Yeah, but at this time the resolution and sensitivity, so resolution is just low because of the long wavelengths and quite limited bandwidth, and sensitivity was quite okay, I would say, but of course a lot lower than that in the near infrared range. Yeah, just some also first scans. Yeah, the spectrometer performed quite well. The sensitivity, the resolution is, I remember, was even below 2 nanometer in this range, and yeah, it was designed in Zmux and optimized, and this is just some interferograms where it starts already to make aliasing effects. Yeah, coming to the result, these are the first results. So this is the very first result for the sample. Actually, it's very interesting that this sample was shown before. Rongsu performed simulation for this sample, and with this measurement we could confirm that at 2 microns we could see through this ceramic sandwich. So it's 2 plates quite scattering ceramics. And just for comparison, the commercial Torlop system at 1.3 could not even see this interface. So the first plate is 300 microns and second one is around 0.5 millimeter. Also for such samples like polymers or composite materials, it works quite well. We could go through this band card chip, look at it, and yeah, this is just for comparison. The first measurement and maybe last results that I had still with Pyroelectric. It was quite improved in resolution. Also, the samples is tilted here by 45 degrees. So actually, the effective depth is higher here. Yeah, so it worked. It didn't give high resolution, but we could get high penetration depth, and it was already of high importance for a lot of cases and materials. Just some other results already that we received a little bit later. Such sandwich can be probed quite well. Also some defects can be observed, and defects in this microstructured ceramics. So it worked well, and also already test OCT imaging at 2 micron appeared. Then some post-processing algorithms, and I made a GUI for the system to operate it easily. This fractional FFT I tried for dispersion compensation, but I think it never was integrated, but it was quite something interesting that Bettina offered. I think these were quite standard post-processing procedures. So then the system was upgraded. The first upgrade, it was like consequences of using pyroelectrics that I said they are AC devices, so they're sensitive to changes. And at the beginning, I had my chopper, so which makes the illumination modulated. I had it at the output of the source, so both arms were modulated, and I saw more or less standard for OCT signals where there is a background and you see modulation on top of it. And then I thought, why do I do it like that if I can put actually a chopper in the sample arm and modulate only interference pattern in which I'm interested in. So like we took out this intensity in reference arm, and then we see only our signals that we are interested in, because delta T would be then proportional to this. And actually it was quite an advantage in a lot of cases. For example, I could go to longer integration times, and it would not saturate my detector. Saturation is not maybe the right word for pyroelectrics, but there is still some floor. And it's just comparison for this standard configuration I had and the configuration I would get if I put the chopper in the sample arm. So it's very simple procedure which allowed to extend dynamic range and got a little bit better sensitivity. That was done, and that was actually something new and interesting with this with pyroelectric detection. You can remove this background just naturally. Yes. The another thing is also quite unstandard, maybe, that it was possible to make OCT imaging in 2 ranges, spectral ranges, using 1 spectrometer and almost simultaneously, not like simultaneously, but just using some spectral filters, they can be switched. So this is first of all because we have very broadband light source, so we have like double wavelengths in the spectrum. And then for standard grating spectrometer, you would have this. So actually, I had another lens before. It was doublet, and I saw some ghost effects, so some ghost interference, and I tried to get rid of it. But finally, it became clear that actually it's a second diffraction order at 2 micron, which overlaps with our first diffraction order at 4 micron, and it can give me some benefits. And some optics was replaced at this point that it's optimized for both ranges more or less, and then I could suddenly see such effects that I see both interferences, that we have interference at 4 and interference at 2. And then by inserting some spectral filters, we can get imaging at 4 and at 2 using the same source and the same system. Of course, at 2 microns, the resolution would be better. I think this is very clear. Yeah, and if we have no spectral filters, it would look like that. So this would be OCT image at 4, and this would be at 2. And these two regions give us different insights into materials. And since they are more or less not completely correlative, but with the same system, it was possible to get images like that when we switch between them or make scan and combine them in post-processing, that we see both like higher, we get both high axial resolution with our near-infrared part and high penetration depth with mid-infrared part. And also with this measurement, it was indirectly confirmed that the simulations of Rong-Su were confirmed. So this is our 2 micron OCT, which is here, and we couldn't see it further. Yes. Yeah, and just about the potentials of mid-infrared OCT for some applied fields. I worked a little bit on like investigation of different ceramics and art objects, and here it can be quite of interest. For example, this is just traditional Austrian pottery, and we could see in, and this a little bit like the black line, which is less scattering, so there are not so strong speckles here. It's due to it's some production layer that they heat, make some thermal treatment of the sample, and then applies the next layer. So it's not an artifact but something real, and it can be then used for some quality control. Yeah, it were very quick tests. Yeah, the same could be more or less in this 2 micrometer OCT, but not. Yeah, then it's of course paints. For paints, I have a feeling that OCT at 2 micron might be better because of scattering. So scattering gives us also some information, because sometimes where mid-infrared OCT just goes through and you don't see scattering, you can't differentiate different layers or different planes, and here near-infrared OCT can work better in some cases. Yeah, so it's just some typical scans. So there's some oil paintings, mock-ups that I made. Yeah, and the field in which we work now is some additive ceramic manufacturing, where we apply mid-infrared OCT, and here it performed quite well. Actually, the resolution of such 3D printer, which prints such samples, is around 35 microns, so it's nearly the same as of our first mid-infrared OCT version, and that's more than enough for quality control and assurance of this technology. Yeah, and we are working on this field currently. Yeah, it's just some other materials that can be probed. So this is also this 3D printed ceramics, which are quite fancy samples. Also some thermal barrier coatings to find some inclusions, and as I said, just normally sintered ceramic sample. Yeah, there is some field to work in, or it might be tablet coatings and some polymer composites. So yeah, of course, water containing samples are quite problematic. Yeah, this is about spectrometry, then OCT, then spectroscopy, how it was integrated, I already mentioned. So actually then we had a second spectrometer here, which is working in a broader range, because OCT was quite narrowband, but with high resolution, and then spectroscopy was operating in a broader range, but with lower resolution. And then, yeah, we collected information from the same point, and I had a quick shutter, which was closing reference arm, and we performed our spectroscopic measurements. The spectrometer use is based on tunable Fabry-Pérot filter. Yeah, and then it was possible to get something like that. So some like sandwich with some picture of different paints inside, and cover it also with some ceramics and with some tape. And with OCT we can reconstruct this the structure of it, and with spectroscopy it was possible to see the picture actually, which is under the wafer. And what we actually see here is just different content of carbon calcium, but yeah, it worked. And this is just how my table looked like for some time when I was preparing these samples. Yeah, this is quite interesting field, and yeah, I was also I had personal interest in this, and I still measure sometimes this time something. Yeah, and just for some more industrial samples, it's also of interest. So that was demonstrated. This correlative imaging was demonstrated for such structures, where there we have some wafer, then some polymer inserted inside, and then another wafer. And OCT can give us the structural information, but of course we cannot differentiate between these different different polymers. And then with spectroscopy, of course, spectroscopy we don't have depth information. This is just chemical mapping, more or less. But we can at least identify these polymers inside. So this is OCT and phase image, and these are spectroscopic images in different ranges. Yeah, and just another interesting thing, that these fringes we have here is some thin film interference. So more or less it's a common path interferometer formed by the top plate and the polymers, thin polymers, and also like applying OCT procedure, we can get the air gap between these two, because and with sub OCT resolution, because spectroscopic spectrometer used for spectroscopy has a broader range. Yeah, these are results I had at this point. So just a little bit about water. I was always thinking that maybe if we go to longer wavelengths, it would be less problematic, but actually it's not true. So I just had filled some water is really a problem here. These two channels are filled with water, and maybe not even fully filled, but it's strongly absorbed here. And recently I just realized that with our OCT system we are at 4 microns somewhere here, and actually it's already minimum in water absorption. So it would be interesting if mid-infrared OCT could have some potential for medicine, maybe for certain samples. Yes. Yeah. These are about old results, and now I will switch to some current results and ongoing activities in our lab. And already when I was finishing my dissertation, I got this idea to try out since as I mentioned, we have no linear arrays, but why to not make like virtual linear array to have a single point detector and make kind of scanning system. So it's simply can be called monochromator, but it doesn't change the difference. Yeah, and there were some papers on this using these polygonal mirrors, which were very fast solutions, and the main goal was to make OCT fast with this scanning. These reports are quite old already, and maybe for current technology state and mid-infrared, it's quite a reasonable solution, which is quite simple, straightforward, but also quite effective, I would say, because point detectors are already quite good in the mid-infrared. Yeah, so the basic theme is here of our current spectrometer. It was designed and optimized in Zemax. So our beam, diffraction grating, then two spherical mirrors that form 4F system, and conjugate a grating plane to the plane of scanner. So of course we can directly rotate grating, but it would be non-linear first of all, and secondary it would be just slow because gratings are big elements, and here we can put scanner which can be rotated very fast. Yeah, so it's just a zoomed part, and in the plane of the scanner we have such pictures that all the wavelengths are overlapped again, so it's like the same pictures would be here, but coming from different angles, and therefore by selecting certain angle of the scanner, by rotating it, we can select the wavelength which then goes to the focusing mirror and being focused on the point detector. So the idea that it can be actually done quite fast enough for mid-infrared OCT, of course. So, and it's kind of kinetic system. Yeah. In contrast to these reports I mentioned with polygons, we put this system at the end for detection, not for elimination, because you can employ similar design to make like kinetic web source, which was done actually before with lens optics. But since we switched to mirrors here because of the mid-infrared, the beam here is quite aberrated already. It's elliptical. Of course, it can be corrected, but the reasonable solution was to make it as a detection system. Yeah, it can be corrected using toroidal optics here and already more advanced design, but this was built using on-shelf components. Yeah, the resolution of the spectrometer is quite good. What we could access with optical design software is around 2 to 2 nanometer for very broad range. The range is from like 3.1 to 4.2 and micrometers. Yeah, and this is just how the signal looks like at in oscilloscope. So yeah, this is just some close to zero delay plane position and outside of zero delay plane position. And here is one scan takes around 40 milliseconds, I think. Yeah, and just some that for calibration I used spectroscopic calibration, and here should be video how it works. So it's like live video, and I'm inserting different polymers inside. So it's not calibrated spectrum. This is sweep in one direction. This is sweep back because we used galvo scanner, and we could see that the absorption line of polymers that can be further employed to calibrate the system. Yeah, this is how our signal on oscilloscope looks like. This is for another source, but just reason to show it here. So the one concern was the linearity of this system and stability, but actually it worked quite well. So this is just 100 spectra recorded sequentially, and it's 18 millisecond per spectra. So we can see that these spectra do not fluctuate a lot, and also interferograms. So the phase is also stable here. Of course, maybe some jittering a little bit because of some mechanical noises. Yeah, it was stable, partly non-linear, but non-linearity can be compensated numerically. Yeah, and finally, when it's integrated already in OCT, that's how the system looks like. So we have already another source, our microscope interferometer. Here barium fluoride lens, and because the band was really extended a lot, I already clearly observed the effects of group velocity dispersion, and that was compensated using window in the reference arm. Yeah, and then we have our scanning interferometer, and such configuration of Fourier domain OCT. So it's still Fourier domain OCT. It's called time-encoded. Yeah, we had some discussion on the naming, but it seems to be a reasonable name for this system. Yeah, again, example how the control signal looks like. Finally, it was made asymmetric this asymmetry of 10% or 90%. So we have a long sweep in one direction, then Galvo goes back quickly, and we record the spectral like that. Yes, and in order to demodulate the signal, I first used lock-in amplifier because Supercontinuum are pulse sources, but recently we switched to boxcar detection, which gave us some additional, so it's more stable and results in better SNR than lock-ins because actually pulse sources are not sinusoidal, and yeah. The low duty cycle sources, for low duty cycle source, boxcar detection is better. Yeah, some just spectroscopic features. So this absorption of PET polymer recorded with this time-encoded system, and this is with Fourier spectrometer, with commercial and quite expensive one. And I would say it's difficult to say where it's high resolution and what is better actually. Yeah, it performed quite well, and these features are used for calibration to calibrate the system. About sensitivity, here there are some interesting things. So the characterized sensitivity of the source is around 80 dB, and actually it's a little bit lower than with Pyroelectric, which I was first surprised, but then I thought that there is like fundamental difference between time-encoded Fourier domain OCT and standard Fourier domain OCT, because in standard system, if we work at, let's say, at 100 Hz, then all the pixels are being active for cameras. So this 10 milliseconds or something. And if we switch to this time-encoded detection, then we have our virtual pixel is being open for only a period divided by n, where n is the number of our virtual pixels or channels, spectral channels, and that makes actually a time-encoded system always a little bit less sensitive. So that's why we have more sensitive detector here, but less sensitive detection that resulted nearly in the same sensitivity. So yeah, that's how it worked, and it worked quite differently for different sources that I tested. I had high repetition rate and low repetition rate sources. It's also something to consider in this case, the peak power advantage. Yeah, about calibration, as I said, I first used these features of polymers absorption and CO2 to calibrate the system, and it worked well. But actually, further I switched to calibration with this Vibrational tunable filter and used these peaks, which makes me a lot of points to make the calibration vector, which is slightly nonlinear, and as a result, I got the resolution of 7.6 micrometer. So, and residual nonlinearities were corrected using amplitude-based correction. So it's more or less similar to zero crossing method. So where we track that the position of the peaks, and we know that they should be equidistantly spaced, and we make them equidistantly, and the function that makes them distances, so this calibration vector is just stored afterwards in the software. That's how it was done, and yeah, we could get quite good resolution for mid-infrared OCT because of very broad range. Yeah, just some first results for ceramic samples, and these are 3D printed samples, and I have to mention that they are very scattering. They are a lot more scattering than that Rongsu simulated and gave me, because also surface scattering is strong here. They are very rough. Yeah, and it worked quite well here. Also, sometimes for higher porosities of around 5%, but already not so effective like for lower porosities. We have various test samples of different structures and sequences to test. Yeah, this is this boxcar detection. it's more or less so the system more or less integrates the pulses, the pulse areas, and you can define the optimal width of this integration window. And yeah, that's why it performs better for low duty cycle sources. It's quite new, I think, to be employed in OCT, and we consider some aspects of this. Yeah, just some very quick comparison of some performances. Yeah, of this time-encoded OCT and our old solution. And yeah, the speed is what I'm trying to optimize now. I made some measurement at 100 Hz with this time-encoded detection, but then I think the spectralization is being reduced and also stability of the galvo scanner. Yeah, but for our current purposes, this system works very well. And we tested also for such green parts, so it's more or less polymer matrix with some ceramics inside. Yeah, and we could detect all the layers. So here it's around half. I think it's 600 or 700 micrometer thick, and this is already sintered sample from these green parts. It worked quite well, and also to detect some defects. This is a quite interesting defect. It's some subsurface porosity variation, which occurs during the 3D printing process, and it was possible to access the depth profile of these variations, which is of interest for this ceramics community. Yeah.
We should allow Ivan 5 minutes for questions.
Okay.
So let's say you have 1 more minute.
Okay, that's good. Okay, I just also should straight there. Yeah, and just to generalize, it's a comparison of this time-encoded system based on low power mid-infrared source. So it's only 16 milliwatts of power above 3 microns, which actually Patrick gave me. I don't know if he's in the meeting now, but I saw him in that he's invited. And this is comparison with the system at 1.3. This is Torlab's system. Yeah, actually that's it. I'm almost in time. Yeah.
Good. Thanks. So let's unmute our microphone and show a sign of recognition of the tremendous work colleagues at RECENT and Ivan are doing here. Thanks, Ivan. Thanks, Peter.
Yeah.
And I'm sure that you excited the NETLAS community into considering all these extraordinary applications which meet infrared but have in OCT. And we have colleagues, researchers, students involved in longer wavelengths. Okay, so any questions, please? We have a couple of minutes for questions. We will close the meeting immediately after 1 UK time. So questions. I see a hand raised. So Manuel, go ahead.
Thank you very much, Ivan. That was a fantastic presentation. Really, really good results. So really well done on all the work you've done. My question is actually more about, since you are effectively an expert in mid-IR OCT, is what avenues, how do you envision the growth in imaging speed? Because that is really the limiting aspect of mid-IR OCT is, well, obviously the sensitivity goes hand in hand with it, but how do you envision, are there any technological challenges that you think, well, it won't be able to go any further, or will it actually be able to go any further?
Yeah, I think it's quite multi-faced question, because it depends on, for example, on source. Also, supercontinuums are quite noisy, and if I would make my measurement faster, it's possible if I exchange this galvo scanner, but then noise would probably dominate. And interesting, what would we will get with this? Of course, if the sources are optimized or we have high repetition rate, it might be already like average these effects. Yeah. Technically, I think, for example, in this time domain detection, time-encoded detection, it should not be a big deal to optimize. These polygonal mirrors can be used. They should have some effect because with polygonal you have axis and your plane that reflects is off-axis. And when you start to rotate it, there is some jittering, and that should have effect on spectral resolution, at least in my design. That's why we switched to galvo, and yeah. But we are working on this further. Yeah.
Thank you. Thank you.
Good. Thanks, Ivan. Any other question? Until we get another question. Looking at your interesting pyroelectric detector, it looked like you had better sensitivity, around 4 microns. Why is that resonance over there?
You mean some sensitivity curve or something?
Yeah, in the spectral sensitivity of the pyroelectric detector, it was more at longer wavelengths. What creates that not resonance? What
Actually,
creates that better sensitivity at longer wavelengths?
Yeah, actually, this pyroelectrics, they are covered. You mean this?
There was a curve before the spectral, and it was enhanced sensitivity at around 4.
Yeah, it's this pyroelectric. It
was that slide with the 2,000 euros cost, where you have shown the spectral sensitivity.
Maybe I didn't understand. Not this one. Here is this.
The slide is behind the just below the spectral sensitivity. You had the price of 2,000 euros. Yes, and you see here in the left.
No, this is not sensitivity. This is just emission of supercontinuum, and this is peak employed. But actually, it's true. It has a little bit better sensitivity at 4 micron, as we can see here. But all these pyroelectrics, they are just blackened on purpose. There is some material which makes them black, and pyroelectrics should work in a very broad range if you make them black.
Good.
So the idea is that just absorb light and make heat.
You have a question from Sasha. Sasha, can you please?
Yes. Hello. Yeah. Thank you. Just a quick question on the wavelength. So you're going to the mid-IR yet? Are there any attempts to go even longer wavelengths?
Yeah, I would try, and I don't know how it would work. But since sources become available, yeah, why not? But as I said, so it might be some limited sample, like class of samples where it can work. So yeah, we are now already at a little bit longer wavelengths. So we have source that goes till 4.6 and something, but the sources till 10 already become available.
But I mean, it's rather like far infrared or something.
And I think there are no really light sources yet into really far infrared. Because this supercontinuum that goes till, I don't know, 18, they are quite of low power. They have 20 milliwatts maybe, and detection can be challenging.
Yeah, well, the concept would of course be quite different. It wouldn't be super continuous fibers in that sense. That's true. Yeah.
Yeah, I mean, quantum cascade lasers could work, but they are very narrow band. I mean, compared to center wavelengths.
There are also other solutions. Okay, but thank you very much.
Yeah.
Good. The time is up, so let's if anyone has questions, please write to colleagues at RECENT. We have recorded it, and we will ask Bettina if we can share it on our webpage, but that will be done later. Now we have to close because there are other appointments. So let's thank the speaker again, and thanks Ivan, thanks Bettina, and have a nice weekend, and yeah, enjoy the rest of the summer.
Yes, and also thank you for opportunity to come a bit more.
That was great. Thanks a lot for.
Yes, thank you, and sorry for a little bit longer talk.
No, that was perfect.
Okay.
Good. Thanks a lot, Ivan.
Yep.
Good. Okay. Bye, everyone.
Goodbye.
Bye bye. Thank you.
Thank you. Bye.
Thank you. Bye bye.
Bye.